Today I wanted to take a look at an intuitive proof for the chain rule that I found. I think, there is a more rigorous and just complex and more correct proof, but it's unintuitive. It's a lot of algebraic manipulation, and I can follow the steps and see that it works, but I don't really feel the intuition there. So this proof is more it's simpler, and you just sort of get it. You sort of get why it's the case when you first start. So we have to look a little deeper into what the derivative. Well, first let me say what the chain rule is. The chain rule basically states that if you want to find the derivative of a composite function f of g of x, you have to that would be equal to the derivative of f with respect to g multiplied by the derivative of g with respect to x. Now we have to look at what a derivative is. So basically, when we're taking the derivative of a function, we're taking a tiny change in x in the input and a tiny change in the output. And we're dividing the tiny change in the output by the tiny change in the input, and basically we're getting a line which is tangent to the function as a whole, which is tangent to the function at that point x that you chose. So now that we know that really a derivative is just a tiny change in the output over a tiny change in the input, we can say that the derivative of this is really df over dx. Alright? Now, the hard part that comes with getting this is we have to account for g of x, which is just this middle step that sort of messes with stuff. But that's a little easy. So again, we find the derivative, or we take df over dg, which is this, and then we multiply that by dg over dx, which is this. These two cancel out, and now we have df over dx. And what always irked me when I initially saw the proof, the chain rule, not the proof, is why do we multiply by g prime of x? What does it even do? And now after seeing this, I just see that it's a translation step that makes it so that we're actually just taking df with respect to dx. Now I'm just going to take a look at two examples, and they're not we're going to take a look at two examples where we do sort of this process. So let's take a factory that produces steel and takes in kilowatt hours as an input. So for every kilowatt hour, we take 4k squared, and we make that number of tons of steel. So we make 4k squared tons of steel. So for every kilowatt hour, we make that kilowatt hour squared times 4 tons of steel. And let's say we have a buyer, B, and he buys steel in bulk. So the function that shows how much he pays for steel is 2,000 times the square root of S, which is tons of steel. So we want to know how much more money we make for every change in K, for how many more kilowatt hours we spend. So, or we use, if we use them efficiently. So first we want to find the change in B, of course. So we take dB. That will equal 1,000 over the square root of s multiplied by ds. Where was I? The change in b is 1000 over the square root of s times the change in s. So we're not gonna turn this into dB over ds for this reason. So we want to find the change in s now, and we're just taking the derivative of that times dk. Now that we have this, we can put this dB all in terms of k, so no need for s's. So that would be 1000 over the square root of 4k squared, because s is just 4k squared, and we multiply that by ds, which is 8k times dk. If we divide dB by dk, that would equal, let's see, that's 2k over 1000. The k's cancel. That's 4000. So dB over dk is 4000. So for every change in k, we make 4,000 extra dollars. So that's our derivative. I would do another example, but I think this sort of illustrates the point. I'm not exactly sure how this measurement might be useful, so I was planning on doing something like, I don't know, tell me in the comments if another example of like, let's see, if the same business, if the same factory could produce copper, and with a different resource, and say W for worker. So for every meter of copper wire, that would be the number of workers squared plus worker. So I'm just making, this is just arbitrary, and we take a different buyer B, which buys copper wire, and he buys it at a discounted rate, not a discounted rate, but he also buys it in bulk. So he buys copper at, for every meter of copper he buys 20. He does $10 times C minus the square root of the copper, also times 10 plus 10 as an overhead cost. Alright, so let's just simplify all of this to 10. No, we should have kept it as is. Too late now. Alright. So of course first we gotta find the change in B. So dB, we drop out the constant and we get 10C, and we do minus 5 over the square root of C, and we multiply all of this times the change in C. And now we gotta find DC, which is just 2W plus 1, so that's the number of workers. Now we just replace all of this. So we take 10 W squared plus W minus 5 over the square root of W squared plus W. Multiply that by 2W plus 1. And then all that times dc. And if we take dB over dc, we should cancel these out. And this would be, this whole expression here would be our rate of change in money per worker. So profit per dollar. The other thing was also the same, except instead of workers, it was kilowatt hours. I think that's what K meant. The comparison I was trying to make, I'm not sure if this is accurate, if this would be a good one. But when does the advantage of adding more workers beat the advantage of adding more of having more kilowatt hours? So at what point does this, how many workers would it take for it to reach 4,000 basically? I don't know if that's how it actually works, if that's what it would actually represent, but still, I hope this video illustrated why it works, and just sort of cleared up why multiplying by the derivative of g is a translation. It's sort of like a translation step. So yeah, thanks for watching.